Hey guys, welcome to the world of Flip Classroom. I'm trying to figure out how to do this. I think we have full screen now. This lesson is on population ecology, and hopefully you'll see in the slides some of the things that you need to know. First thing is to be able to define a population, which is all of the organisms in a certain area that interbreed. By the end of this lesson, you should learn what characteristics you can use to describe a population and what factors affect those characteristics. Each population has its own characteristic demographics, and there you see the word demographic defined as the data that describes a population. These can be things such as size, density, distribution, patterns, and age structure. So we're going to take a look at some of those. There are two practical ways to estimate a population size. You can imagine that it's not very practical to try and count everything within a population. So the two practical ways that you'll be responsible for knowing are plot sampling and mark recapture sampling. You probably already have an idea of what these mean just from their names, and you've certainly seen lots of mark and recapture on nature shows on TV. Here's plot sampling. This estimates the total number of, I don't know why that popped up, of individuals in a population. Here they're looking at all of the plants within a given grid, and then they just multiply the area up for the larger area to estimate how many plants would be in the larger population. Mark and recapture here, unlike the plot method, would be used for mobile animals. Here's our little butterfly. He's been labeled with a number, and if somebody catches him again, that can tell them something about the number of that species in the area. Here's a little slide. We'll go into more detail. This is in our textbook. Whoa, slow down. I don't know why it's going so fast. Population distribution patterns. We're going to watch a video on this. Nearly uniform, random, and clumped. Again, these are pretty obvious. All right, here we go. Oh, wow. Okay, per capita growth rate. This is every per capita here. Capita is, every head. So per capita growth rate is equal to the per capita birth rate minus the death rate. You could also include with birth, you could put in immigration. With death, you could put in emigration. But this is the formula, just if you factor those out. All right, this term, zero population growth, is usually talked about as the acronym ZPG. Really popular in the 60s. If we all only had just 2 children, then our birth and death rates would be equal, and we would not overload the ecosystem by increased population. This might be behind the rationale for the Chinese having their one-child go back. Come on. Okay. This might be why the Chinese... I have no idea what's happening. Oh, boy. Okay. At any rate, if the population is not growing, they say it's ZPG. Again, 2 kids equals 2 parents, ZPG. And perhaps in China they were trying to do this so they didn't overload their population. 2 types of growth curves, and these are usually plotted. Oh, go back. Come on now. As exponential and logistic growth. And you know about these already, I think, I hope, from Bio 1. And you may have even seen these for yourself when you were in the doctor's office. When you were younger, they can estimate your height as an adult based on your rate of exponential growth when you're a child. So on the left-hand side, there's the exponential curve. And go back, come on. And on the right, the logistic growth, sometimes described as looking like an S. Logistic growth, if you look at the bottom part of that S, it does look a lot like exponential growth. But at some point, something happens in the environment, some sort of limiting factor, maybe food or water or space or light, is going to slow down that rate of growth until it hits that little dotted red line at the top, which is known as the carrying capacity. later on we'll see that carrying capacity is can be labeled with the letter K. So carrying capacity is really the maximum amount of any population that a certain environment can take. So for instance, here in Galveston, if we had in our natural state, the carrying capacity of the environment here is probably maybe around, like, I don't know, 50 people. All we have is brackish water. Not too many people could live here naturally. That would be the limiting factor, and the point of maximum growth would probably be around 50, and then that rate would start to slow down and give that S curve for logistic growth. Here it is again, looking at time versus population size, and there's our carrying capacity with a capital K, and they describe the limiting factors in general as being environmental resistance. Some reason that you can't just keep growing non-stop. You've all heard those statistics about how bacteria could grow unchecked and just be a matter of days, I guess, before they would take over the world, but they do get checked. They run out of food. All right, this is out of order. This is looking at 3 types of survivorship curves. This is based on data from a life table for each of these species. In the classroom, we're going to take some of that data and try to plot it out and figure out if the data we're looking at is from a type 1, a type 2, or type 3 type of survivorship curve. The 1, 2, and 3 here are just random labels. I don't want you to ever come back again. Don't show this message again. All right, 1 there. And again, these are just random labels. Is for a type of organism that stays at a fairly constant rate and then drops off later in its lifetime. And humans here are a typical example of this type. Here's our little squirrel here for an example of number type 2 survivorship curve. These guys just steadily decline until there's none left in their group. That brings up another word here. Cohort is the name of a group. They would follow a group of squirrels from the time they were born till the time they died to get that data, and that data would be representative of that particular cohort. You, as a class of juniors, have been a cohort since you came in as freshmen, and we could take data from you from freshman year to senior year, and that would be data for your cohort. And the 3rd type of survivorship curve here shows an oyster. There are many of these at the beginning, and they drop off rapidly. So really what you have to memorize is type 1, type 2, and type 3. Here's a Dall's sheep. These are beautiful animals that live in Alaska. Here's their type of growth curve, and I want you to tell me tomorrow if this is type 1, type 2, or type 3. You can see that they actually stay fairly stable for a long time. For about 7 years there, the population of that cohort remains stable, and then they start to die off later from wolf predation, old age, and sickness. Here's the same example as the first slide. Squirrels. Starts out with a lot of them, and they die off at a fairly steady rate. Although here it's interesting to compare the males and females. Females hang around a little bit longer. So tell me what type of survivorship curve this one is. And here we've got another type of survivorship curve for our little frog. About 100 of these in this cohort, and drops off fairly quickly.